As a review before hearing some of the interviews, let's recall how the derivative was derived from the problem of finding tangent lines. Suppose y is a function f of x whose graph is a green curve. We want to find the tangent line to the curve at the point p, a, f of a. First, let's consider a nearby point q, x, f of x. The slope of the secant line pq is the change in y, f of x minus f of a, over the change in x, x minus a, or rise over run as you learned in high school. This is also the average rate of change of y with respect to x over the interval a, x. Now consider the slope of the secant line PQ as Q approaches P, or the average rate of change of y with respect to x over smaller and smaller intervals of x by letting x approach A. This would be the same as letting the change in x, or run, approach 0. The limit of the slope of the secant line PQ is the slope of the tangent line at P. Or another way to think of this is that the limit of the average rates of change of y with respect to x is the instantaneous rate of change of y with respect to x at x equals to a. Notice this limit is the derivative of f of x at x equal to a, or f prime of a. So we can interpret the derivative of f prime of a as 1, the slope of the tangent line to the curve y equals f of x at x equals to a, and 2, the instantaneous rate of change of y equals f of x at x equals to a. For more geometric representations of the derivative, feel free to watch the video from 3 Blue, 1 Brown linked below. To understand the importance of the derivative and its diverse applications in Calculus 1, we asked a handful of Trinity students and professors about how they use derivatives in their daily coursework or research. Here are their responses.
We focused on using them a lot in doing locus plots for control systems or whatever. They appeared in thermodynamics, a little bit in statistics or whatever, but like the concept of like finding the rate of something, you're going to come across that in any type of physics.
If you have a particle which is moving around from one place to another, its velocity is the derivative of position with respect to time, and then its acceleration is the derivative of velocity with respect to time. And the most fundamental of the laws that we study in introductory mechanics, Newton's laws of motion, relates acceleration to laws of nature. And so being able to connect this idea of position, velocity, and acceleration to a law of nature then gives you a way to determine motion from fundamental principles.
In economics, generally we will make some assumptions, so maybe there's a price for the good that I'm producing, and I'm trying to figure out what quantity to make, and maybe as I make more, my costs start rising to make each incremental unit. I'm going to want to make those first few, but at some point, right, it's not going to be worth continuing, and so I'm trying to maximize my profit, and so that entails writing down a profit function and using a derivative to help me maximize that function.
The data that I use, it's the number of mammoth. And there's this phenomenon that says those mammoths, they live mostly near British Columbia. They have been disappearing. And there's people are afraid, conservationists are afraid that they might completely disappear out of the face of Earth. So there's this conservation effort that's being made. But what is making them disappear in biology is called the Alley effect. That is, the size of that population of mammoth has reached a critical mass where no matter what people are doing, it's keep disappearing. So they're studying mechanism on how to reverse the process. And that change, basically that decrease in the number of mammoth, it's part of, you could say, an application of those derivatives.
We can also look at really complicated networks of reactions. And so I do environmental chemistry research. And when we're thinking about atmospheric chemistry or modeling all of the chemicals in the atmosphere, that's really complicated. And we have to use derivatives to make simplifications and approximations. And so that allows us to model sort of the global atmospheric chemical processes and figure out answers to things like the ozone hole or how these molecules are contributing to climate change and stuff like that.
And it turns out that there is a lot of math required to make pretty pictures and to make computers make pretty pictures. And so derivatives are really important, particularly in their geometric interpretation. That the derivative of function is defining tangent to a function. And particularly for a three-dimensional surface, it becomes really important to know what's called the normal at a surface. So the direction that the surface is pointing. And those normal directions matter for lighting calculations, for doing simulations, for a whole wide range of things.
For example, a capacitor, the charges go on to a capacitor and it builds up over time. And that's a time-dependent behavior. You need time-dependent mathematics in order to understand it. The Ohm's law equation for a capacitor exists, but it has a derivative in it. And you have to understand derivatives to get anywhere with circuit theory.
If you have a car driving along on a highway, one of the things that you can see out the window are lines. Now, I know, again, I have my speedometer there, but just imagine that this was a dash cam video and all you're seeing in the picture is the lines. So we know that video is taken at a specific frame rate. In other words, how many images per second are grabbed. And we also know the length of the lines on the road. I can look at the way the lines move in my video. In other words, how many lines are passing per second, or based on the length of the lines, how quickly are they passing through a specific point on my video. And I can then do a calculation and literally get the speed directly from those images, from those sequences of images.
We then asked the students and professors to talk about what they thought was the most important topic covered in Calculus 1. That is, what they believe is one of the biggest takeaways or consequences of the derivative from the course. Here are their responses.
One of my favorite topics from Calculus 1 was the idea of optimization and using critical points to find the maximum and minimums of a function. And those have tons of really fun, interesting applications.
I think, again, that geometric interpretation of a derivative, of what a tangent is, what an acceleration is, or the second derivative, and then how that can be applied to both real-world simulations, or real-world situations, and simulations of those real-world situations.
Calculus 1 is in some ways the first more rigorous math class that students take. It's an introduction to more abstract ideas. And one of the best things you can learn about it is the process of solving abstract problems. How do you take a problem, represent it in an abstract sense, and use the machinery of mathematics to solve it?
I really think the concept of a limit and the concept of really kind of pushing yourself to understand edge cases, like as you're going, approaching limits to zero or limits to infinity. I think that was super helpful for developing kind of quantitative intuition about things.
I think it was the idea that, of a rate of change. This, going all the way back to Newton, who formalized it all. How do you understand mathematically when something is changing? I always think of rockets. I think of rockets going up, rockets coming down, the parabola, the idea of a rate of change, the idea that you can compute a distance based on, knowing a few things about its acceleration, about its, about how much time is elapsing. It's a powerful tool. And so that basic rate of change idea stays with me as the most important thing.
And one of the things that I think is worth stressing for what you want to learn in calculus isn't always just the mechanism for doing it. It's true. I do a fair bit of by hand derivation, but a lot more of it is the understanding what it means, right? The making sure that the concept of instantaneous slope or rate of change or how you view the derivative, making sure that sinks in.
I think truly the most important thing is being able to apply what you've learned instead of just being able to solve the problems you put on the page, being able to take them and use them when you need to.
I would encourage all students who are studying these topics to try to look for examples in real life so that they will gain this more intuitive understanding.